All right, grade 11s, let's start with doing a compound interest question again, where we compare one plan with another plan. And this is something very useful with financial planning, and we're going to use the graphing calculators to make sure that we're happy with those. We have a landscaper who needs to borrow $20,000. One bank offers an interest rate of 10.5% per annum compounded semi-annually for 5 years. Another bank offers an interest rate of 10% per annum compounded quarterly for 5 years. Which is the better plan? Very important to compare. Let's do it by hand first of all. We're going to look at the 10.5%. So we'll call this bank 1 in blue. And we have an interest rate of 10.5% compounded semi-annually, so our I is going to be adjusted. It is 10.5% as a decimal divided by semi-annually would be 2, which gives us an I semi-annually of 0.0525. The N will also be adjusted because it is semi-annually for 5 years, which would be 5 years twice a year, which would be 10 times. The amount. He borrows $20,000, 1.0525 to the power of 10, and the amount is 33,361. Nope. Hold on here. Yep, 33,361.92. So the interest he would pay Bank 1 would be 33,361.92, which is what he owes the bank. Subtract what he actually borrowed. So the interest would be $13,361.92. It's a comma or a space. There we are. The second bank, slightly lower rate, but it's compounded more often, and we know that that can work against us in a loan. So Bank 2, our I value is 10%, and it's compounded quarterly. So we would divide by 4. 0.025. The N value is 5 years, but quarterly, they're going to compound the interest 20 times. The amount of this loan, $20,000, 1.025 to the power of 20. When we type that into our calculator, we will get $32,772.33. The interest is the $32,772.33. Subtract his initial loan, $20,000. It will be $12,772.33. In the course of 5 years, that's a fair bit of interest difference. The difference in interest is 13,361.92 take away 12,792. It's $589. And I don't know about you, but that's a fair bit of money. Let's look at the graphing calculators where we could have compared this very quickly. Let's compare the two. First of all, turn it on this time. Isn't that wonderful? We want to go to the financial application. So I use the blue apps button. Number 1 is my financial. What we didn't write down yesterday, that it's the TVM solver. You may want to write that down. So we have on, apps, financial, TVM solver. And we get the screen. Let's fill in the data for the first scenario, the bank number 1. Bank number 1. So N is for number of years for compound problems. The number of years is 5. The interest rate for bank number 1 is 10.5. The present value is the loan that he wants to take. So he gets that in his pocket. We're going to leave that as a positive number. We don't have regular payments for this problem, so we'll leave that as 0. Future value is going to be the amount of the loan. We're going to get the calculator to find that for us. Payment per year, we're just going to leave that as a 1. Compound per year, this is important. For the bank number 1, the blue question, we're going to do it semi-annually. Put a 2 there. So we want to know the future value or amount of the loan, and we're going to get the calculator to solve that for us. This is where we type in alpha, enter. So I go to future value. Alpha is a green button. Enter. It will give it to us as a negative because that loan is going to come out of our pocket. We're going to pay it back. Notice it's the same amount as when we calculated by hand. Let's look at the other bank. And enter the information there. So we go back up. It is 5 years the same, but the percent is 10%. Present value, we're also taking a $20,000 loan. We're going to come back here in a minute and get the calculator to solve future value. Leave payment per year is 1. Compounding is different. It is quarterly. So we're going to put a 4 there. Back up to future value. We're going to find the amount of this loan by typing in alpha, enter. So green button right there. Alpha, enter. Negative 32,772.33. Yes, when rounded. Perfect. So we've got the same 2 answers using a graphing calculator. And if you were comparing different banks and different rates compounded at different ways, this graphing calculator would be a very speedy tool to use. This is not particularly practical the way we did Christoph's example, where he owes the entire loan as a lump sum after 5 years. He's got to come up with $33,000. Most people take loans or invest as an annuity, where you have regular payments, often monthly, but we rarely have a one-time deal where you take an investment and you cash it in all at once or make a one-time investment. Those scenarios would be simple or compound interest. When there are regular payments, monthly, where you're investing regularly or paying off a loan regularly, we call that an annuity, and it is much more common. Let's have a look at Donnell. Donnell is depositing $50 into an account every month to save towards a cruise. If she has an account that gives 8% per annum, compounded monthly, how much will she have in 5 years? This diagram can be helpful thinking about what happens with Donnell. Right now, she makes the decision. She's looking at cruise brochures. She's thinking, wow, I'm going to get $50 together this month and put it into my account at the end of the month. So she puts in $50 after a month. And that $50 sits in that account for 5 years, and it earns interest. What it will earn is $50 times 1.08. Oh, it's compounded monthly, so we've got to change our I value. 0.006 repeating to the power of 5 years monthly would be 60. So that one's going to earn a lot of interest. In 2 months from now, she's going to put another $50 in. And that $50 is going to earn interest for a long time as well. A little less, but it's going to be 1.006 repeating 59 times. And then in the third month, she's going to put another $50 in, and it's going to earn interest. All the way down till the very last $50 she puts in. It doesn't earn any interest at all, and she takes it out at the end of 5 years and goes on her cruise. The amount that we calculated each time was $50, 1.006 repeating to the number of months. To find her total, we would have to add each one of those little bits. She would have her $50 plus the one right before it would be $50 times 1.006 repeating to the 1 month, plus on and on we would add until we get to the black, the red, and the green one that I have on the board. 1.006 repeating, sorry, that's a 0, to the 58, add to the 59, and last. That's a lot of calculations. We have 60 different calculations to do and then add them all up. So that total would be $50 plus $50.30 plus 73.50 plus $73.99, actually 74 when you round it up. And the last one, oops, $74.50. We would have to calculate each one of those. I've only done a couple of them and add them all up. Notice that this is the sum of a geometric sequence. So we can use that formula to develop our monetary formula, which might look a little bit different, but we know the sum of a geometric series is A times r to the n minus 1 over r minus 1. If you're used to that formula and you like it, you go for it. We're just going to rewrite it with terms a little bit different, but it's the same thing. The amount of this annuity, or the sum of all of those deposits plus their interest, is going to be the initial value A. Well, in this case, it's a regular deposit of $50. Her initial value is $50. So in this particular case, it's our $50. We're going to call it R for regular payment. Your rate of growth is 1 plus I. And we know that the I has to be adjusted depending on how it's compounded. To the power of n, that's the same. Subtract 1 over r subtract 1 is, don't write this down, 1 plus I. Subtract 1, well, we've got two 1's there and they cancel each other out. We'll be left with an I. So you will notice on your handout that we have the very same geometric sum of a geometric series formula, just written a little bit differently to use our values for money. Let's refresh ourselves again that I and N changed depending on the compounded rate. So if you are getting payments every 6 months for 7 years, you are paying twice a year for 7 years, it will be 7 times 2, which is 14. Our I value again is 12% per annum compounded semi-annually. Notice that these two things match. If you have 12% a year, you would divide that by 2, would be 0.06 twice a year. Every month for 2 years is going to be 2 times 12 times a year is going to be 24. 12% monthly, the decimal 12 divided by 12, you're going to get 1% each month. Every 3 months is the same thing as quarterly. For 5 years, your end value will be 5 times 4, which is 20. 12% compounded quarterly is decimal 12 divided by 4, which is 3%. Every year for 12 years, isn't that nice? You get 12% compounded annually, nothing has changed. Every 6 months, which is twice a year, we're going to take our interest rate and cut it in half. Decimal 0.35, semi-annually for 30 months. How many semi-annuals are there in 30 months? Well, semi-annual is every 6 months. So they are going to compound your interest 5 times. Be careful with ones that are just a little odd. Every 3 months is the same as quarterly. So we're going to take our 10% and divide it by 4. The number of times the interest is compounded, 42 months every 3 months. So 42 divided by 3 is 14 times. Every month for 8 years will be 8 times 12, which is 96 compounds. 18% compounded monthly is 0.18 divided by 12. You will get 1.5% every month, just to refresh yourself. Jeremy is in grade 8. He has a paper route and wants to save for his college education. He determines that he has $100 per month to put into an account at 6% per annum, compounded monthly. How much will he have at the end of 5 years for his college education? First of all, we need to check if our I and our N are different than annually. So he can get 6% per annum compounded monthly, so both are adjusted. 6% monthly is 0.06 divided by 12, which is 0.005. The N is 5 years monthly, 5 times 12. Now we want to look at this annuity. I'm going to write it with the money numbers. If you wish to write it as a geometric series way, that is absolutely fine. But I'm going to have the amount is the regular payments times the rate to the power of n, subtract 1 all over I. The amount of this annuity. Now this happens to be saving towards, it's not a loan, but it's all the same thing. His regular payment is $100. This rate of growth is 1.005 to the power of 60, subtract 1, over 0.005. When all the dust settles, you really need to try these with your calculator. Use brackets. Be careful. You will get $6,977. I don't want to drive you crazy, but I really want you to be able to use these graphing calculators. So we're going to go back to the financial. So to get their apps, financial, TVM solver, and here we are. We're going to put this information in. This is where it's a little bit different with an annuity. We don't put n as the number of years. N is the number of compounds. So we're going to put a 60 in for n. Make a star there because it's different for annuities. 60 is the number of times they're going to compound his interest. His interest rate is 6%. So that you type in as you're given. Present value is the amount of money Jeremy has right now. He's got nothing. His payment, it's going to come out of his pocket. So I would do negative 100. Payment is the same as R, and we're going to do negative 100. I don't know if this helps you, but it helps me. So that when he gets this final answer, it's going to be a positive number. The future value is what we want to figure out. We've got the calculator to do that in a moment. Payments per year. How often does he put money into that account? He does it monthly. And it is compounded monthly. At this point in your life, those two things need to match. We want to know the amount of this loan after he's been at it a while. We want to go to future value and do alpha, enter. So alpha is green, enter. It will give us $6,977. Notice it's positive because that's the money he is going to get. Lars wants to have $60,000 to give his daughter when she finishes university. What a nice guy. He decides to make equal deposits in his bank account every 6 months. As soon as you see something going on in a regular way, you have an annuity. This is not a one-time deal. Lars has to put it away in a regular way. Ending 3 years from now, how much should he deposit in his account that pays 8% per annum, compounded semi-annually? We want to know what his R value will be. How much, if he has a certain goal in mind. He would like to give her $60,000. $1,000. We don't know the R value. We know the I is 8% compounded semi-annually. So if it's 8% per year, it would be 4% semi-annually. The number of deposits that are made and the number of times that interest is calculated is every 6 months for 3 years. So that will be 6 times. So we are going to type this into our equation. And solve for R. $60,000 equals R times 1 plus I, 1.04, to the 6. Take away 1 over 0.04. Again, we're solving for R. You're peeling away all the extra numbers. We're going to multiply both sides by 0.04. So 2,400 to get R by itself, I'm going to divide both sides by nasty square bracket. I have a regular deposit of $9,045 and 71 cents. Does that make sense? Is it reasonable? If he wants $60,000, he is putting $9,000 in 6 times. He is going to be putting money in himself that is less than $60,000 and earn some interest. He will add up to $60,000. It is a very reasonable answer. Let's check with the graphing calculator again. See if I can get it so you can see it. There we go. The N is the number of times interest is calculated, which would be 6. The interest rate is 8%. present value is he's got nothing. The payment is what we're going to get the graphing calculator to find. Our future value, $60,000. It is paid and compounded semi-annually, so both of those numbers are 2's. We would scroll back up to the payment option. It's going to be a negative answer because it's coming out of Lars's pocket. We're going to do alpha, enter $9,045.71.